Assalamu alaikum students. Today's our lecture is going to be about simple pendulum. Let us define the simple pendulum first. A simple pendulum consists of a small heavy mass M suspended by a light string of length F fixed with the upper end. Oscillating simple pendulum length of pendulum, which is the sum of the length of the string plus the radius of the metallic bob, as shown in figure. Now this is the figure of the simple pendulum. So this is the length of the string plus the radius of the bob is also included. So this is the length of the string plus the radius of the bob, and this is the mass of the pendulum represented by M. As you can see, this is how a simple pendulum basically moves to and fro and goes back to its mean position. When such a pendulum is formed, it means position and starts oscillating to and fro about its mean position as shown. Let the bob of the pendulum of mass m having a weight w is displaced from its mean position to a point A. Let us move it from point O to a new point by applying some force, which is point A. So here we go. This is point O, this is point A, new position, and point C is the fixed position. Now these are the angular parts. So theta is the angular displacement and x is the arc length from point O to point A, and L is the distance, or you can say length, of the pendulum. Weight x vertically downwards direction, tension is in the string, which is T. We have resolved W into its components. So here we have weight, which is vertically acting downwards, tension is inside the string, and we are now converting the weight into its component, which is mg cos theta, which is the horizontal component, and mg sin theta, which is the vertical component, because this theta was same because two lines were passing through a single line which is parallel to them. Now in this case we can say like this: if two lines and one line is basically getting crossed to them, then these two angles will be equal to each other. So that is why in the same manner we are taking theta equal in that case as well. So in this case, we are resolving the forces. So this T is in opposite direction to mg cos theta. So they will cancel each other out. So T is equal to mg cos theta. And applied force must have a restoring force, but in opposite direction. But what is the restoring force in this case? Yes, it is actually the mg sin theta. So what we have done is the restoring force is equal to minus mg sin theta. As you can see, it is in the opposite direction to the applied force. That is why the negative sign is there. So we are putting it equal to the applied force, where ma is the applied force and the restoring force is minus mg sin theta. If we cancel out these m, what do we get? We get a is equal to minus g sin theta. Now, if we consider this theta to be very, very small, what happens then? Again, the pendulum basically vibrates too much with a larger angle, but if we consider the same angle to be very, very small, in this case, we are assuming that theta is very, very small, then in this case, sine theta will be approximately equal to angle theta. It means acceleration depends upon sine theta. When theta is very small, sine theta, and equation 1 becomes a is equal to minus g theta. So in this case, we can see that when theta is very small, to point O will be very near to point A, and arc OA, that means this distance, will be a straight line. Instead of an arc, it will be a straight line. And triangle OAC will be a right angle triangle, and x over L will be equal to sine theta over theta. Equation 1 will become A is equal to minus g x over L. Now what happened over here? How did theta becomes x over L? So let us revise this concept, that as we know that theta is equal to s over r, where s is the arc length and r is the radius. If we consider this same pendulum as a circle right over here, then The distance from the center to the circumference is L, or we can say it is equal to R, which is the radius, and the distance from here to here is the arc length, which is equal to S, or we can say S. So here we can say X is equal to S and R is equal to L. So that is why instead of theta, we are putting X over L instead of theta. So the new equation becomes A is equal to G over L. Just by rearranging the previous equation, we get A is equal to G over L into X. Now G over L, both values are constant because the value of G is 9.8 meter per second square, and the value of L does not change throughout the experiment. During the motion, G and L remains constant, so we put G over L is equal to omega square. That means a constant value, or we can say angular velocity square. Hence, if we put constant over here, it will be A is equal to constant minus X. If we remove the constant, we will get A is directly proportional to minus X, which is the equation for simple harmonic motion. This is the equation for simple harmonic motion. So motion of a simple pendulum is simple harmonic motion. Now let us define the time period, which is equal to T is equal to 2 pi under root L over G. Let's see how it is being driven. The time period required by the pendulum to complete one vibration is called time period. Now, because it is a time period for one vibration whole, so we'll take theta is equal to 2 pi. By definition, T is equal to 2 pi over omega. We remember from the definition of omega, that means angular displacement over time is known as angular velocity, which is omega, and theta is basically 2 pi, and it basically cover a whole time period or whole revolution. So there is a time period t. So if we rearrange this equation, it will be t is equal to 2 pi over omega. But omega square was equal to g over L, or omega is equal to under root g over L, taking under root on both sides. Then equation 1 will become, that means the same equation will become t is equal to 2 pi under root 2 by pi under root L, sorry, g over L. Now in this case, if we rearrange this equation, it will be t is equal to 2 pi under root L over G, which is the same equation for the simple pendulum. Now from this equation, what we have found that the equation shows the longer the pendulum, the greater will be the time period. And the second point, which is going to be the time period of the simple pendulum, is independent of the mass because there is no m in this formula. I hope you enjoyed today's lecture. Inshallah, we'll meet again. Allah Hafiz.